I am Julius Sumner Miller. I teach physics. Consider this astonishing thing. I have here a little board, and here a sheet of paper about the size of an open newspaper. Now I put the board under the paper in this fashion, with a little bit of the board sticking over the edge of the table. And now I'm going to deliver a sharp, impulsive blow to this end of the board, and we witness a very dramatic thing. Nothing moved, and we are led to ask, why is it so?
Hello there. Well, once again, a fascinating number of experiments with Professor Julius Miller. And I'd like to begin, Professor Miller, with asking again, why is it so? How did it happen?
Didn't you expect, when I hit that into the board, to have the whole thing topple over?
Well, paper has no weight to it.
Right. But here is the answer. We live in a fluid, like a fish in the sea. And few ever witness the dramatic properties of the atmosphere. Here we have a paper about 20 by 30 inches. 20 by 30 is 600 square inches. On each square inch, there rests about 15 pounds of push, the weight of the air. 15 pounds per square inch is atmospheric pressure at sea level, roughly. 600 square inches times 15 pounds per square inch, 9,000 pounds. There rests on this paper, Sanders, 9,000 pounds of load, 4.5 tons in American tons. Now, what did Newton say about massive things? Do they not want to stay
as they are?
As at rest. So when I tried to move this 4.5 tons by a short-lived impulsive force, it refused to be moved. You want to try it?
I'll try it.
Good. Here, I'll give you a fresh board, and we will put the board under the paper. And be careful not to tear the paper, because I don't want the air to leak through, you see? And now, remember, if I pushed on that ever so gently, watch what happens. Do you see the whole thing comes up?
Yes.
But Newton said, if you try to accelerate this mass, it doesn't want to be accelerated, which is tied up with the first law and the second law. So deliver a sharp blow there with your fist.
I might end up on the floor, I think.
No. Look at that. So you did it. You see, there's nothing mysterious about it.
Not at all.
As long as one understands why it is so. Isn't this dramatic?
If we lift up this piece of paper, we're lifting up 9,000 pounds?
No. This calls for another discussion.
Well, you gave the people who've been watching this program a number of problems.
Hold on, before we go to the problems. You know the surface area of the average human being is about 3,000 square inches. 3,000. That is, if you took a cadaver and spread the skin out, it would be about 3,000 square inches. 3,000 square inches, 15 pounds per square inch, that's 45,000 pounds. That's over 22 tons. 22 tons of load on you all day. Is there any wonder why, at the end of the day, you go around quite exhausted? Back off a little. I have to fix my burner here. We are showing some more atmospheric stuff.
Well, before we go to the questions, I want the people to learn the answers of these problems.
Now, do you see, this is a point of view with which I am quite hostile, giving the answers. I don't like to give answers until people have thought about the questions. But I'm a charitable soul, you see. The first one was the can with the 3 holes. Let's see what we had. You remember? Here is a tall can in which 3 holes reside. And we asked some questions about how does the water come out. So if you back off, I will show it a little. Just back off a little bit. So, yes, I am drawing. Here is a hole at 1/4 of the way down. Here is a hole at half of the way down. And here is a hole at 3/4 of the way down. And the can rests on that level table. And then we said that there was a constant head of water here, so you understand water in here. And we said first that the water emerges when the plugs are pulled at velocities increasing like that because of the increased pressure. Yeah. And I said that was a consequence of Evangelista Torricelli, you remember?
Yes.
And then I asked the more important question, what is the path of the water from each orifice to the tabletop?
This is where I went wrong.
Well, everybody says this. I'll draw it lightly. Everyone says this. You see the most range from the lowermost, and a middle range from the middle one, and the least range from the uppermost. This is reasonable, but it happens to be wrong. Let me just switch my water here. It happens to be wrong. I am going to give the right answer. Watch. Dramatic. Range. Range less, and identical. Isn't that absolutely astonishing? So the uppermost and the lowermost orifices give us identical ranges, but less than the maximum range which comes from the middle orifice.
And why is this so?
Oh, this calls for a little elaborate algebra, and if some are capable of the calculus, it is done more simply and directly, so I leave it for those who wish to learn the mathematics. But isn't it a pretty thing?
It is indeed.
More than that, let me say one more word. This maximum range from the middle orifice is exactly equal to the head of water. Isn't that delightful? Now you're going to say, Julius, of what use is this?
I wasn't.
Well, you know better now.
I've learned the lesson.
Euclid had a student. And after the first proposition in geometry, the student said, Master, and what shall I gain by learning your geometry? Whereupon Euclid called his slave and said, Give him a drachma, for he must make money at our cost. You see.
This is of no interest to you.
I have no interest. I am interested only, Mr. Sanders, in the intellectual gymnastic, of which there is much more needed.
Indeed.
So the can with the 3 holes is settled. The paradox of forces. What was that?
Well, I remember we had 2 1,000-pound weights.
Right, 1,000
gram weights, rather.
We put 1,000 grams on there, it reads 1,000. When the system is at rest or moving uniformly up or uniformly down. When we put 2,000 on, it reads 2,000 under the same conditions. Will you set those down, please? Let me change my water again. I hope no one is troubled by this gymnastic, but we need this operation. Then what was the question?
If
I put the balance in a horizontal line, the scale like this, and with a little pulley here and a rope, and a little pulley here and a rope. And then I put one of those 1,000 grams on this side, and the other 1,000 grams on this side. And what was the question? What does the balance now read? And remember, I informed you a little bit by saying there is 1,000 pulling that way and 1,000 pulling this way. And some say they annul each other, so it's 0. And some say they aid and abet each other, and it's 2,000. And then there are some bold and daring creatures who say 1,000. And I disposed of that as wrong.
Yes.
And then the question was, is this one right or is this one? And we must dispose of this one, and this one is the answer, but I give no reason. I give no
rather
reason.
Aggravating, I should say. Can't you just explain a little of it?
Yes. Do you remember I put a little rectangle on the board in an earlier show, and in it I put those things you have to understand if you wish to understand nature, and one of those was Newton. So if one learns a little of Newton, he will be happy. Good. Next one.
The Case of the 2 Eggs by Julius Sumner Miller.
Right. Notice. Doesn't it sound like Sherlock Holmes?
Yes.
See, the case of the engineer's thumb, the case of the solitary cyclist, the case of the 2 eggs. Here. What was the question?
Your wife has boiled 1 egg and mixed it up with a number of unboiled, fresh eggs.
Right.
Now you have to find the boiled egg and I suggested by dropping or by shaking it.
Oh,
and you said that's
vulgar.
Rather
I
ridiculous.
think I appraise that attack as vulgar. Watch. We are going to invoke some beautiful mechanics. I don't know which is which. I picked them up at random, but watch, I'll spin these. Do you see that does not? Oh, yes, it does. It spins, right? No, it spins pretty good, doesn't it? Beautiful. Now I'm going to try to spin this one. Oh, doesn't this one spin much more nobly?
It does.
Yes, look at it. Look at that.
That's a noble spinner,
A noble spinner, right. I say that is the hard-boiled one. This one has its spin motion damped out by internal friction and some other strange forces which arise in circular motion, referred to by those who don't understand it too well as centrifugal. But is it not clear that we have separated them?
The unboiled egg has its spin motion damped out by
right.
internal
I
frictions.
love that word. That's the proper word. Damped out by internal friction.
That's
because that's
word.
what friction is. Viscous friction is damping. Right. You've done beautifully.
It was your word. I hate to admit.
Yeah, but hold it. Another question about eggs. Let's not run away from it. Supposing now you had in the refrigerator some eggs, some of which you suspect of being bad, and they're mixed up with some which you know are good. You wish now to determine the bad ones and the good ones. Quickly.
Well,
leave this as an exercise.
Does a bad egg go thick?
Let's not discuss it. Let's not discuss it. I want to know how to separate the good ones from the bad ones on short notice. This is an exercise for those who are listening. What's the next problem?
The 2 sliding blocks.
Yeah, the 2 sliding blocks. What did we have? You know what we had. We had a board that we can raise on edge in this fashion, on which we put a block. And we raise this end of the board, and pretty soon the block slides. Right? Pretty soon it slides.
Right.
Then we try the other block alone, and pretty soon it slides. And if we agree that the surfaces adjacent with the plane are identically rough or identically smooth, will not the blocks slide at the same angle?
Yes.
Right. Supposing it's 27 degrees. Good? Now I put the blocks together. Are not the 2 heavier than the one alone?
Yes.
So then when I raise this end of the plane, I put this question. Do these 2 slide sooner or later? Let me give you arguments in support of both. Oh, I think they slide sooner because they are heavier and want to move quicker. Oh, no. They slide later because they are heavier and want to stay longer. Are not both lines of argument pretty?
Yes, they are.
But
fairly reasonable, I think.
Right, but both are wrong. Both are wrong. The blocks together slide at the same angle as the one alone. Now, isn't that a strange thing?
It is.
Yes.
Are you going to explain why this is so?
No. Again, we draw on Newton. You see how much reliance we must put on Newton's mechanics. Beautiful thing. Beautiful. You know what Lagrange said of Newton?
No.
There can be but one Newton, for there is only one universe to establish. Newton did it. So
you have one law to establish.
Notice how we check them off. I feel guilty of malfeasance and misfeasance. Why? We are not doing properly by these demonstrations. They should have deeper inquiry. The colliding spheres. Colliding spheres. What did we inquire? Watch. I take one up, one goes away. There's a little other action there with which I do not wish to be concerned. But your question was this. When I let 2 down, 2. You asked, why cannot 1 go away with 2v? Let me say a word more. When 2 go away, each of mass m and possessing velocity v, the momentum of the pair is 2mv. If 1 went away with 2v, we would have the product of m and 2v, and since m and v are commutative, as we say, the momentum would be again 2mv, which it was before, and things would be all right. Nature would not be ravaged. But I said, I never have found. Indeed, were I to find it, Newton's bones would rattle, because 1 cannot go away with 2v. Why? Oh, I hate to tell you this, because there are some young people who should be made to ponder this until their brains writhe in agony. Reminds me of Newton. You know what Newton said? I must give up thinking about the moon, for it makes my head ache. Isn't that just wonderful? Yeah. So the young children should have their heads ache. But I'm charitable. The answer lies in energy. If 1 went away with 2v, there would be more energy after the collision than before, and this we cannot have. Okay?
Where does the energy go?
Oh, the energy goes? Did you hear some sound?
A click.
A click. Right, sound. Therefore, you have some acoustic energy out of the mechanical. After numerous collisions, there is some heat energy developed. Energy is lost in friction on the track. I suppose there is some electrical energy there residing in the molecular structure. Much, much deep stuff here, if one wished to explore it. Yes. Have we answered all the questions?
We have.
Now where do we go?
Well, I'm intrigued by this, and I hope some of the people got some of the questions right.
Yeah. Oh, we'll give. Let them write us. Invite them to reply to us how they did.
I think we're probably going to get letters from you asking more details for these.
Right, all right.
So we'll extract from Professor Miller before he goes back to America the
Watch
answers.
what we have. Atmospheric pressure. I have here a can in which some water has been boiling.
Yes.
I have boiled it for some time so as to be sure the air has been driven out. Now we have in the can water vapor and a little water, right?
Mm-hmm.
I am going to stopper up the can. I'm going to stopper it up. And I'm going to put it down there. And doesn't it look harmless, innocuous, and idle? Listen, 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 listen. Nature is taking hold. Do you hear it? Oh, it's dramatic. It is music to my ears. It is like a symphony. I am going now to hasten the process. I'm going to pour some cold water on there. When I pour cold water on there, it condenses the water vapor inside. That water vapor goes back into the liquid state. There's some empty room in there, and the atmosphere will, I hope, come and crush it to death. Watch it. How is it? How is it? Look at this side of it. Look at this side. How do you like that?
Lord.
Oh, yes. Do you see what would have happened if I did the same to you? Isn't that enchanting? Look at that. I am so delighted with this that I'm going to do it again. Oh, you see? Whoa, oh, I need my protection. Do you see how delightful a thing this is? Absolutely delightful. Do you see how the world must get excited about it? Listen. Oh.
It's rocking on its own accord.
Oh, yes, look at it. Oh, listen. How do you like that? Are you stirred by it, Sanders?
I'm fascinated and slightly worried by it, I think.
No, don't get worried. Nature... Oh, look at this. Let me turn it for the camera. Look here, look here, look here, look here. Do you see it? Mm. Do you see the atmosphere crushing its very soul? Watch it. Oh, now we fixed it. How do you like that? Look at here. Isn't that something?
It really is. I hope you're not going to do the same with the glass.
No. Let me show you what I'm going to do with that. It's more of atmospheric pressure. Do you see I took the burner away. There we have a vessel, a round bottom flask with water boiling, and I'm shutting off the gas here because we have no need of it further. Are you agreed? Are you agreed that this water is becoming silent?
Yes.
Let us leave it a little while and go elsewhere. Have we, as we thought it out, accomplished our purpose here? We'll return to this.
If we could.
I want that to get quiet. Come down. Oh, before we go, I have a little memorandum. This is to throw a little lightness into the otherwise serious drama. You see? I wish to ask you, manhole covers, you know them? You find them on the street?
Yes.
They are round. Why are manhole covers round, Sanders? Now, don't tell me they are round because the holes they fit are round. I've had that answer. Why do you think they're round?
Does it equalize the pressure?
Has nothing to do with it. Let me interject. Is the question interesting?
Yes, I've never thought of it.
Oh, this is it, you see. Nobody thinks much about anything.
I have seen square ones, but I must admit most are round.
I don't think you have seen manhole covers square. Indeed, it would be a dangerous thing to make them square. I leave this as another question. Why are manhole covers, why are sewer covers round? Does not this question strike you as utterly feeble and innocuous and simple and trivial and mundane and vulgar even?
No, it doesn't. No. I'm afraid it's interesting.
What I'm saying it for is this. Don't you see that I am hoping that everybody, especially the youth, will observe a little more closely and become a little more inquiring? See, why is a manhole cover round? There is a very good reason.
And
let's get out
You
here.
promise that you're going to give us the answer before you go back to America?
Someday. Notice I have the classical Magdeburg hemispheres, which you read about in all physics books. Let's evacuate some of the air. We are pumping out some of the air. These are two metal hemispheres which fit together smoothly.
Can we fit them on?
Well, we'll get them apart and see what they look like after. I am taking out some of the air between them. They fit together on smooth faces, not screwed together, just faced together.
Like putting two cups together.
Right, right. Now, we have taken out some of the air. And now, hold that system, will you please? I am going to put a hand, don't touch that valve. Don't touch that valve. I am putting on a handle here for one of us to pull. Now do you see what happened? Let me draw it on the blackboard. Step back a little. Here it is. Here is a cup. And here is another one whose face fits the first one very nicely. And here is a handle. And here is a handle. And we have taken out some of the air from inside. And now what is holding them together? The push of the atmosphere. We found that everywhere, didn't we?
Yes.
Watch how stout the push of the atmosphere. Is not the push of the atmosphere stout?
It is indeed.
Indeed. 15 pounds per square inch, and all one needs to do is to get the facial area of this thing to find the force with which they held together. But now, a steady pull cannot pull them apart. On whom shall we call for assistance?
Newton,
Newton! Of course we call on Newton. Without it, mechanics would have no foundation. When you wish to break a stout string, and it does not break under a steady pull, can you not break it by a sudden impulsive pull?
Yes.
Let's do the same. There we are. You see, we called on Newton. Let me show you now another one. Come up. We are dealing with gases, fluids, of which gases I remember. Fluid is the generic name for gases and liquids. The astonishing property of the gases which constitute the atmosphere. Here I have a little balloon. I'm going to put it under a bell jar, so, and then I put this bell jar atop it, and now I'm going to reduce the pressure in the bell jar. This allows the gas in the balloon to expand and expand, the molecules getting farther and farther apart. What am I hoping to demonstrate? Gases are characterized this way. They fill completely the container they occupy, which is to say, that when you are in St. Patrick's Cathedral, a thimbleful of gas, if it were otherwise empty, the cathedral, a thimbleful of gas would fill it. Isn't that amazing? Conversely, all the gas in St. Patrick's Cathedral can be put into a thimble. You squeeze it in. So, watch this gas fill completely the container. Let's pump it down. What do you see the balloon doing?
Expanding already.
Yes, look at it. And if this stuff of which the balloon is made has enough elastic strength, it'll fill and fill and fill. And I have a bell jar as big as a steel drum, and I fill it. Look at that. Isn't that dramatic? Look at that. Gases fill completely the container they occupy. Is not this proof of it? We may run into a little snag. Yes, do you hear the change in the pump? Let us shut it off, please.
It's laboring a bit.
Yes. Now. What has happened is this. The balloon has filled the little orifice in the pump plate so that no more air can get out.
Pumped out, I see.
Right. So, therefore, nothing further will happen. But isn't this dramatic? How much time do we have? Have you any idea?
No, I don't, Inspector Peck.
Well, we should know. Next
demonstration.
We have 5 minutes. Oh, yes. Oh, let's go back here. Let's go back. Do you see that this is pretty nearly quiescent? Pretty nearly. There is some heat energy in the soot and in the vessel itself, so the water is boiling sort of feebly.
Yes.
But remember, what do we have? We have water there and water vapor above it. But has not the whole thing cooled down substantially? I took the heat.
It has, yes.
I'm going to make it boil very viciously by putting some cold water on here. What does the cold water do? Condenses the water vapor inside, reduces the pressure, and water then can boil at a lower temperature. Indeed, at the top of Pikes Peak in America, water boils so cold that you can wash your hands in it. Don't you have a mountain like that named after some Polish patriot?
Kosciuszko.
Good,
not as high, I think. But,
yeah, high enough. Go there and try it. Indeed, at the top of Pikes Peak, you cannot boil potatoes in an open pot. Can't do it. They never cook. Water never gets hot enough. And you like tea? You can't make tea at the top of Pikes Peak. Water never gets hot enough to brew the stuff out of the leaves.
It is apparently boiling, but there's no heat in it.
There's
no...
I don't like the sentence. It is really boiling, so the first part was wrong and the second part was wrong, too. You're making every effort, Sanders, to flunk this course.
Will I stay in the class, do you think?
Oh, because I have affection for you privately. Watch now. Look at that water boil. How do you like that? Isn't that terrific? Now, if time allows, we shall come back to this in an hour. In a whole hour. The water will be so cold that you can... you wash your hands in it, and it'll boil again. Let's get back here. This is the case of the can with the two holes. The case of the can with the two holes. Oh, where is my nail? Yep. Oh. Here is a can sealed up. We wish to know the following. I make a tiny hole in it. A tiny, tiny hole. Do you see? Tiny hole. Good. I think this can has something in it, a liquid. Now I try to pour the stuff out. Are you agreed? It does not pour. Why? Because the stuff is trying to come out that hole, and the air is trying to go in, and they can't both do the same at one and the same time. Right?
Yes.
Therefore, I make another hole. Right? Right?
Right.
What will we expect now?
Well, it will pour much easier.
Do you see it pouring?
Yes.
Right. The holes are very tiny. Now, I want to tell you a story about this because it's absolutely enchanting. For several years now, there goes by my house on Sunday morning a little boy named Sam. When we started, he was 6 years old. I make it a point every Sunday to be out to discuss my programs. Why is it so? So this Sunday morning, we are talking about my program on atmospheric pressure and why we put two holes in a can. Sam agreed that this was a very wonderful and dramatic thing, and he closed the discussion by saying, Professor, I'm so very glad you did that experiment because that is something I have not quite understood all my life.
That's very sweet.
Isn't that wonderful?
Yes,
6 years old. But do you see, we have here maybe a beginning Faraday, a Michael Faraday, or a Rutherford, an Ernest Rutherford.
An inquiring mind.
Right. How's our time?
Well, sir, I think it's almost time for us to finish off the program. We have a couple of minutes left.
Couple of minutes. Yes. Let us explore something. Let's go to my toys. My toys. You know I am interested in the physics of toys. Here is a 10-cent automobile. Oh, no, 10 cents in America. 1 shilling here. 1 shilling. Yes, I complained about it. She asked for a shilling. I said that's 11 cents and it's a penny more than I should pay for it. I want to know, what can I do with this in a physics sort of way? I do the following. Watch. Does not a child do that?
Yes.
I have given rise to some mechanical energy due to a friction torque which made the wheels turn. The wheels are geared in turn to a little flywheel whose axis lies along the whose plane is along the long axis of the car. This flywheel has all its weight in the periphery. Therefore, it has large moment of inertia. And when I get it spinning very rapidly, it has a large measure of rotational kinetic energy. Doesn't that look strange?
For a child's toy.
Oh, yes. Oh, do you see how much physics and drama and beauty lies in a child's toy? So you store energy in it by doing work, and then the car can go. Isn't that wonderful?
It is.
What I'm saying is this. If a child was exposed to the beauty and drama of this with a little information also, could you not start him at the earliest age?
Professor, a very good point, I think, to finish the program. Thank you very much, Professor Miller.
My pleasure.
And another program next week.
Thank you.